everyone, and welcome to the our first society seminar for this academic year. And what's a better way to have the inaugural society seminar of this year than with having my dear friend and colleague and really awesome scholar, Eliassi Rad, give this society seminar. And the idea of society seminar is, the way we spell it out, SOC parenthesis AIEEY, AI in and for society. And Tina clearly has her entire academic record of publications. She's been a leader in this space, not only connecting different disciplines, whether it was network science and AI. She was doing graph algorithms and machine learning on graphs before it became cool that everyone should do machine learning on graphs. And Tina has been a front runner in this and really looking at some foundational work. She's currently the inaugural Joseph E. Aoun Professor of Computer Science at Northeastern University. And as I said, how awesome she is. She's that awesome that the president of the university decided to endow her professorship with his name. And not just that, his name, as the inaugural person to carry his name is as Tina to her professorship. So, she can't do anything wrong with that, right? So if there's anything, anything you want to get done at Northeastern, you just go to Tina, and she'll make it happen. And prior to Northeastern, she was at Rutgers University as an associate professor of computer science. Prior to that, she was at Lawrence Level, National Labs, where she also received an Outstanding Mentor of the Year award, 10, 15 years ago. And she truly is an amazing mentor and a friend. We've known each other for many years. She was saying earlier, since the time we were young. But one of us is still young, and that's for you to figure out. And she's also received the honor of Network Science Society Fellow. She won the Lagrange Prize on complex systems, especially recognizing her work at the interface of AI, privacy, and ethics. I'm sure there's many more. And today she's going to talk about pure talk the matter in the age of generative AI. But there's another presentation she has called Just ML. And I think that was the most fascinating title of a talk I've seen, Tina. Just ML is like, justice, ML for what is fair and just ML, but also it's just ML from an algorithmic perspective. But today we will learn about the truth. Tina, please.
Thank you so much for that excellent. Thank you. So thank you so much, Nitish, for that lovely introduction, and thank you all for being here. I know it's the beginning of the semester and lots is happening. So as Nitish said, I'm here to talk about the elephant in the room. And what I'm going to do is I'm going to start with motivating the work first. And first is Human AI Society. So in 2021, we wrote a Nature Perspective piece where we talked about how we live in societies that are algorithmically infused. That is, the very fabric of our society is co-shaped by our human behavior and what the algorithms are doing. And we discussed three challenges that you see up there. First is the insufficient quality of measurements, and second is the complex consequences of mismeasurement, and third was the limitations of existing social theories. And in particular, we need to reflect on what to measure and what not to measure. In a seminal paper that Zaid Omermeyer and his colleagues had in Science 2019 article, they showed that in the US, predicting healthcare costs rather than severity of illness is not a good idea, because in the US, we don't spend the same amount on our different subpopulations. And so you are not going to get what you want by measuring a proxy as opposed to what you really should measure. And in that work, we also highlighted this feedback loop that is going on in terms of not just economics, where you go to Amazon and Amazon recommends something to you and you buy it, and then the algorithm is like, oh, this is a good thing, and then it goes round and round, or politics, but also in terms of our social relationships, right? So many people are meeting via these online dating apps. Those dating apps are taking data from the real world And based on that, you make your recommendation, you go on a date, and it changes our acceptability of certain societal processes. And so this feedback loop is extremely important. And then more recently, in an AI journal article, we talked about human-AI co-evolution. That is, now with generative AI, we have even moved beyond this algorithmically infused societies to where we and these algorithms are co-evolving together. And again, this feedback loop came up, right, where the user's choices produce training data. Those training data goes into the recommendation algorithms that make suggestions. Those suggestions influence your user choices, and round you go. And so a concrete example of this is this picture. My husband and I, we were in Athens, Greece this summer. And the picture, the reality is Acropolis is a very popular tourist destination, right? You see all those people behind us. But with my little iPhone on the Photos app, there is a feature called Cleanup. And with the Cleanup, I could get rid of all the people, right? And of course, if I was still on social media, the thing that I would be uploading is the cleaned up version, right? And then the AI systems will believe that the Acropolis is not a popular tourist area and that you can have shadows without people, right? And it's just not me. There are all these people who are out there and they're cleaning up their photos and they're uploading them. And so this issue of the feedback loop between the data, the algorithms, and what we do is extremely important. And in that paper, we talked about some of the challenges in this human-AI co-evolution, from the scientific to the legal, to the social political. And I just want to highlight the scientific challenge of this bidirectional causality, which you see up there. And so if you think about causation, in the past few decades, there have been two dominant camps here. There's been the Judea-Pearl's camp, and there's been the Don Rubin's camp. If you're a computer scientist, you probably have studied Judea-Pearl's structural causal models. If you're a statistician or a social scientist, you know of Don Rubin's potential outcomes framework. And neither of these two camps has the right technical prowess to do this kind of causation that we want in this human-AI co-evolution. With Donald Rubin's approach, you can't even do it. With the structural causal models, yes, you can do extensions to it, but in high-dimensional data, with high-dimensional data, you cannot use it, and it will struggle in terms of scalability. So for the students here, if you're interested, this is an open area of study that would have high impact. So then this gets us to epistemology in human-AI society. For those of you who know, epistemology is a study of knowledge. So what is it, how we get it, and how we can tell if we really know something. And so some pertinent questions to ask in our human Gen AI societies is, what do you know? What do your interlocutors know, whether they are a chatbot or whether they are human? And how do these interactions affect the society as a whole? And for those of you who are interested in graphs and networks, what you're seeing here is a hypergraph. Every blob is a hyperedge. Every blob is representing a communication, and the nodes that are in it are the participants in that communication, right? And clearly, when you talk to somebody, perhaps it may change what you know about the world, right? Maybe I can convince you that the COVID-19 virus was leaked from a lab in Wuhan and not, occurred naturally. So these are all really interesting questions to ask in this era that we are in. And so one of the things is, what do your interlocutors know? And one of your interlocutors is a large language model. So what does a quote-unquote large language model know? And I'm putting "know" in quotations because obviously large language model is not a human being, but it's easier to say "no" as opposed to a much longer sentence here of what it has stored in its internal probabilistic knowledge. So this work is with my postdoc, Gurman Savchicians, and you can download the preprint online. And so since we're going to talk about large language models, I'm going to go briefly through what they are. So this is an accurate picture of a large language model. If you take anything from this talk, let it be this picture. And this picture is not by me, it's by my friend Henry Farrell at Johns Hopkins University. This is, as I said, it's an accurate depiction of a large language model. We have the monster that gobbles up data, mostly from the World Wide Web. It is the monster that's responsible for hallucinations and regurgitations. Then we put a human face on the monster when we fine-tune a large language model for our purposes, and we add this happy face at the very end for the human user, and this is it. Now let's go through 4 steps that are essential steps here. One is collecting massive data. So the lots of data that they collect are mostly online. The large language models that you use every day are trained on approximately 20 trillion tokens. So this is a lot of tokens. And tokens could be words, parts of words or sentences, characters, etc., depending on how they tokenize it. Different large language models tokenize the words differently. So if the word depression happens a lot, some language models call depression a token, and other large language models break it into subsets. So DEP would be one token, and so on and so forth. And so as you know, there are a lot of cases in the courts right now about AI copyright versus, it's copyright infringement versus fair use. And about 54.5% of the cases is actually about text generation. So large language models, whether it's default models or chatbot models. And perhaps a market-based solution will come about here the same way we went from Napster to iTunes and Spotify, but we're very far away from that. And while we're here, I would like to emphasize that these, we hear a lot of hype about how amazing these models are, and yes, indeed they are, but without our human data, our history, our expertise, our culture, without that being inputted into them, these models will collapse. They will not perform as well as they do. And so this data oftentimes is referred to as asset, and unfortunately, it's not valued as much. And when I was talking to David Otter, who is an MIT economist, he's saying it's not valued as much because anything that's distinctly human is not valued by the markets, right? But you have to understand that you play a big part in, for example, ChatGPT working the way it's doing, because it is using your data and your friend's data and the data from your father, your mother, your grandparents, et cetera, et cetera. So then we get into the learn to predict the next word or phrase. So for example, you have the best thing about AI is its ability to, and it looks at its lexicon, and let's say the word learn gets the highest probability, so it will return learn. And these probabilities are extremely small because its lexicon is very large. And it's important to know that this part is not supervised, right? This is the self-supervised part. It's basically a very large-scale pattern recognition model. And to do this, it also does contextual word embedding. So it will have basically for every phrase, it's embedding it as a vector, because computer scientists, we love vectors in Euclidean spaces. And here I'm showing you in 2D, but normally it is much higher. It goes from like 256 to 16,000 dimensional space. So 16,000 numbers to store the cheese-loving mouse, for example. And all of this also depends on the context size, and the context size can go anywhere between 8K to 100,000 tokens, and the context size allows the large language model to have some memory and be coherent. So within this context, what did I see? It's like a window that you're looking at, but because of this, then it can parse a sentence like this. Buffalo, 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 right? All of that, right? So it's able to distinguish between buffalo, which is the proper noun, which is the city in New York, buffalo as a noun, the animal, and buffalo as the verb, meaning bully. And so then what happens is there's this supervised fine-tuning for whatever task you want. And the supervised fine-tuning often involves these very big deep learning models with many, many, many parameters, like hundreds of billions of parameters. A lot of the state-of-the-art large language models have anywhere between like 1.3 billion to 1.8 trillion parameters. And if you even think about like 100 billion parameter, if you're an old AI person like me, AI is all about search. So what I'm doing is I'm searching a space that has 100 billion dimensions for a point in this 100 billion dimensional space that will minimize my loss function, right? Many things could go wrong, but they seem to, between some generalization and a lot of memorization, they tend to do well. So along this line, a couple of years ago, we did this work on life to vec that maybe you saw, it went viral, where our idea was that every person has a story, and a story is a language, and we have these large language models. Can we get people's stories and build a pre-trained model, that monster, but from good data? The monster in part is a monster because of all the data on the web that is not curated. We had really good data from Denmark. So if we have surveillance capitalism here, they have surveillance socialism in Denmark. And we had data for 6 million citizens of Denmark over 12 years. And so what we were able to do is take that data, come up with a symbolic language, then feed it into a transformer model, which is the heart of these large language models, and then be able to have these kind of compressed representations of each individual's life. And then we could look at these individual representations in this embedding space. We had a lot of health and labor data, which was very helpful, and then fine-tune it for things like early mortality prediction, whether somebody was going to leave Denmark, and some personality tests. The reason this work went viral was because of the early mortality prediction. And the model does very well in whatever measure. We had multiple measures of predictive accuracy, and it was like close to 80%. And so a lot of insurance companies took notice, and it was like, and there was a lot of these articles about, oh, AI can now predict when you're going to die, etc. But they didn't look at exactly what we were doing. So what we were doing was we were looking at people between 35 and 65 and whether they were going to pass on in the next 4 years. So we first built this pre-trained model that through this, and then we had data for people between ages of 35 and 65 and whether they were going to die in the next 4 years. And so, and then we did a lot of auditing on it. And one of the things that came out was actually labor data is very helpful in figuring out whether somebody was going to perish in the next 4 years, not health data, because health data, for those of you who worked on it, is very, very noisy, right? So obviously, if you're an electrician, and of course, if you're a male, because males believe that, like, oh, I can jump over this ravine, nothing will happen to me, right? Females usually are like, maybe not, right? So it was a computational social science study, and a lot of it was like, oh, well, labor data, like if you're a manager, it's less likely that you're going to die in the next 4 years than, all other things being equal than if you're an electrician. But, you can actually use this notion of, and like we're trying to now use this for another project that I have about can we predict evolution of certain fish, stickleback fish, where you're like, what's the life story of a lake, right? We can't write it for a fish because fish don't live that long, but you can then try to build get the data from a lake, give it to a transformer model, and try to analyze it to see what happens. So that's the part about fine-tuning, and then you want to align its output to the desired behavior, right? And this is where the content moderation comes in. This is where the reinforcement learning with human feedback comes in. So in all of this, you never hear about how humans are involved. And I know that Karen Howe was here, and she was talking about how humans get exploited through this process, and I very much admire her work. And so despite all of this work, despite the humans that label data, that rank data, etc., you really can't remove all the bad things that are going on from the data that these large language models see. So on the occasion of the International Women's Day back in March 8th of 2024, with a group of scholars from around the world, we published this report for UNESCO on how misogynistic and sexist these large language models are. And I won't reiterate a depressing story here. I will just note that the misogynistic calls are coming from inside the house, because a lot of these large language models are trained on data from countries where we don't think they're treating their females poorly, right? This data isn't coming from parts of the country, from parts of the globe where we think are bad to their females. So it's a window on what we are. So now at this point, you're like, oh, large language models are so 2022. What about reasoning models? And yes, there are lots of reasoning models if you haven't encountered them, right? So you give it a prompt, instead of just giving you a plain response, it will talk about what it's exactly doing. And if you look at the commonly used reasoning models, it goes from basically what I'm calling engineering on steroids, where you will have this multiple rounds of supervised fine-tuning and reinforcement learning, to using like specialist models that have been trained on, let's say, logic to produce high-quality synthetic data, to having these kinds of knowledge distillation models where compress like a big teacher model into a student model, but it still remains, the question still remains about what does the model know. So to really know, this was all the prelude to this, to know what a model knows, what happens is you probe it to find out what's going on. You basically examine it to see what's happening. And there are lots of papers here, and of course this is not an exhaustive list, so if I don't have your paper up here, my apologies, send me an email, I'll add it to the list. And so one way of probing a large language model to figure out how well it does in separating, let's say, truth from falsehood about the veracity of a statement is basically like in-context learning. So you can do a zero-shot prompt or a few-shot prompt where you give it a particular prompt, you treat the large language model as a black box, and then you will find out the probability of, for example, whether it believes the statement to be true or not. So here, the statement we want to see whether it's true or not is the city of Agadir is located in Morocco. That statement is in fact true, and we're like, select one of the following, it's a multiple choice, and you see that, for example, the probability for selecting one, the statement is correct, is very high, and this probability distribution is over its lexicon, right? So this is the black box model. The one thing with the black box models is that so if you're using a default model which hasn't been trained for the interaction, then you can do the prompt, which I'm showing up there. If not, for chat models, some of the chat models allow you to have like a context prompt. Some of them, like Gemini, don't allow it. So then you can add in, if you know something, to it. Now, with zero-shot prompting, it's very sensitive to the wording or the ordering. So if I were to change, for example, correct and incorrect to true and false, I would get different results. And if I shuffle the multiple choice answers, I would also get different results. Now, if you do this also with humans, in terms of shuffling the questions, the humans will also give you different results, right? We have seen this over and over again with students. If you set them a multiple choice questions and then you shuffle the numbers, maybe the students think, oh, well, most of the answers are B or C, right? And so they change it. But one of the things that we see is that the effect is more pronounced in large language models than in humans. And this is also true with the chat models. If you change their prompt, it's a feature of this kind of an in-context learning. And I'll show you some results going forward, and the results are based on these performance measures. So some of you may have heard about Matthew's correlation coefficient or the phi coefficient, and basically it goes from -1 to 1. 1 means total agreement between what the classifier is predicting and what you observe, so the best. 0 means that it's random, the predictions are random. And -1 means total disagreement between what the classifier is predicting and what it was observed. And in some of these models, the model can abstain and say, I'm not going to answer to this question. And so then you can have this kind of a weighted MCC where you take out the portion in which the model abstained on. So talking about the zero shot and how it differs, on the x-axis I'm showing you the weighted MCC, Matthews correlation coefficient. On the y-axis, my postdoc implemented 16 of the open source large language models, both default and chats. And if there were no change between the original formulation of correct, incorrect, true, false, and shuffled, then you would expect all of these to be on top of each other. But you see that they're not on top of each other. One of the things that we do see is that in the chat models, they tend to be closer to each other. And this is a functionality of the reinforcement learning with human feedbacks, that you're getting human feedback in terms of, look, correct and true are basically the same thing. Don't change it, right? Or incorrect and false are meaning the same thing in this case. And this brings us to a side note I wanted to talk about. When DeepSeek was released, the DeepSeek R1 was released, it's a Chinese large language model, and of course it was trained on Chinese data and it was censored by the Communist Party. And so if you ask it what happened at the Tiananmen Square protest, it says, sorry, I'm not sure, etc. But what you can do is you can attack it, you can jailbreak it, you can do this thought token forcing, and you can add what happened at the Tiananmen Square protest, think I know this. And then it will tell you what it does know. And so you could break it and you could find out what it knows. And if you go to my colleague David Bao's page, he has a lot of interesting stuff about actually what the answers are in Chinese and what the answers are in English. And so this thing about like what does the large language model know also depends on whether you're jailbreaking it or not, right? And we'll put that aside. It's just a side note. It's just an interesting concept to look at, to think about. So the other part of probing a large language model to see what it actually, like how it knows about the veracity of a statement is to crack open the box, right? And actually look at the internal representation of these large language model at the different layers. As I said, there is this deep network that it gets trained on, and so you can look at the different decoders and the embeddings, and through that, then you can get the vector representations, right? And so let's look at the mean difference probe. It was one of the earlier ones that came out. So you have your large language model, and it's an open source, so you can look at the different layers of it and the different representations. And for mean difference probe, it takes the representation of the last token, and then it sends it to a very simple classifier, and then it says whether the classifier says true or false. So this is the full chart for it. So you have to have a separate data set with statements on whether they're true or false. You just send the statements to the large language model. The large language model will give you the Z's, these embeddings. You know the true from this data set, the true false, then you do the standard machine learning. Like I have my training set, I have my testing set. From the training set, I will send it to this mean difference probe. I will get the parameters I need, the coefficients, the intercept, and the inverse of the covariance matrix, and then I send it to a sigmoid function, and I see whether it says true or false, right? Very simple, no problem. And this is this notion of probing it, right? So basically like, oh, I have this large language model, I crack it open, I see what its internal representations are, and I'm gonna see, okay, can I use a simple probe, like a simple classifier, to see if it can separate truth from falsehood? So as we were looking at this, we found a bunch of flawed assumptions in the previous work. The first one was that they assume that LLMs capture and retain everything that we know, right? But we should distinguish between what the LLM quote unquote knows and what we know to be true, right? There is a distinction there to be made. The second one is that the truth and falsehood are bidirectional, like this way true and this way false. But that is not the case. There are statements that are neither true nor false. For example, this statement is false is neither true nor false, or the present king of France is bald is neither true nor false, right? So that's another one. Then the other notion was that they're assuming that all the veracity probes, all of these classifiers that are doing these probes of separation are producing calibrated probabilities. And the way to think about calibrated probabilities is that they're estimating they're accurately estimating the true likelihood of the phenomena that you are trying to represent. And that is not the case. And then the other one was that every token or statement is either true and false. And that is not true. Like, well, how would you say, what is the value of a punctuation mark? Is it true? Is it false? And lastly, that a priori we know where the signal for the veracity is in a statement. But how would we know that? So if I have the statement, hey, the city of Hamel is not located in Sweden, is this correct? Which token is it that is the most important token that would say that this is true or false? So since we found these flaws, we're computer scientists, we introduced a new method where we address these things. So instead of assuming that LLMs capture and retain everything that we know, we sample only statements that high support from the large language model. Instead of just assuming that truth and falsehood are bidirectional, we learn separate classifiers. So we learn is true and we learn is false, right? Something that is not true does not necessarily mean that it's false. I've been married to a logician for 32 years, believe me, it's a thing. So, and then in terms of all veracity probes provide calibrated probabilities, here we use conformal prediction to try to quantify the uncertainty and be able to produce statistically valid regions of prediction. So here, the way to think about it is that you can then identify regions, and you would say, depending on how you set the hyperparameter, you would say, okay, every point that falls into this region, 9 out of 10 times it's true, right? Or 9 out of 10 times it's false if the region is representing falsehood. And then instead of saying every token or statement is either true or false, we also learn for neither. So we learn three binary classifiers: is true, is false, and is neither. And lastly, instead of assuming that a priori we know where the veracity token is, we use multi-instance learning. So multi-instance learning, you label an entire bag as true or false or neither, right? Instead of just having one token. So you have the statement and you are looking at all the different representations that you have for the different tokens, and you're saying that this is true or not. And so that's SAML for sparse-aware multi-instance learning. And this is what I was saying, which is like, if I have the city of Agadir is located in Morocco, then for the city, I have the internal representation for whichever particular decoder or level that I pick, layer that I pick, and for all the other words. And that's what I give to SAML to be able to separate it out. Now, when you think about probing these large language models, it is not wild, wild west. If you decide to come up with a probe, there are clear criteria for measuring how good your probing is. The first one is called correlation, or oftentimes information or accuracy, which is if you train your probe on a particular data set, D-train, then it should do well on the D-test, assuming that they're coming from the same distribution. Then there's generalization, that if I train the probe on D-train, then it should do well in terms of predictive accuracy on data from also different domains. Now different, we can talk about what different means here and how different is different, but that it should generalize, especially to neighboring domains. Then there's this notion of selectivity, that if I train a probe on D-train, so it should not assign true or false labels to samples where the truthfulness is absent or undefined, right? That it should be able to say, I don't know. And then there are two other things. One is manipulation and one is locality. So if you really think that there is this notion of this way true, this way false, and this way neither, and I have these internal representations, if I were to roll the internal representations toward truths, then the probe should detect that, right? And if I roll it toward falsehood, then it should detect that it's more false than before, right? And with locality is that if I were to roll these internal representations, which are just vectors in Euclidean space, toward a random direction, then nothing should change. So it should be sensitive to that. So, as I said, so Gurman instrumented 16 different large language models, both default and chat models. In here, we also have large language models that weren't specifically trained on English. So Mistral is French. It was trained on French and on English data. And the Gwen models are from Alibaba. And so they were trained on Chinese data and English data. And for this, as I said, you need to have a third data set. So Gurman generated 3 data sets. One is city locations, one is word definitions, and one is medical indications. And so in the data, we have both affirmative statements, like Paris is in France, but we also have negated statements, like Paris is not in England. And here are some examples of the things that appear in these data sets. And I'll talk about how we come up with the neither statements in a minute. You can download the code and the data, and you can look at them. In fact, the data has been more popular than we expected. A lot of people are downloading it from Hugging Face. And at the end, I will also have a QR code where you can download the entire presentation, the slide deck. So I'm going to show you this picture. So we're trying to learn is true, is false, is neither. We learn these binary classifiers, and then we put them together in the multi-class classifier. And here what you're seeing is on this angle, on this line, you're seeing probability of neither. On this is probability of true going this way, and on this one probability of false going this way. And the region that is red is the conformal prediction region for falsehood. That is, every dot that falls in there, the model believes that with 90% confidence that it is false. And the blue region is true, and this greenish region is neither. Now, the dots that fall outside of these regions, the white region is the abstain region. And this is an important point in terms of distinguishing between neither and abstain. So when you go neither, it means that the large language model, quote unquote, knows that it lacks definitive evidence to determine if the statement is true or false, and it gives it neither. When it abstains, it doesn't like any of the choices you've given it. It doesn't like true, it doesn't like false, it doesn't like neither. It doesn't fall in any of them, right? And so every dot that you see here is a dot in the test set. The color shows the actual ground truth of it. So obviously these models aren't perfect, the probe isn't perfect, etc.
Even the ground truthing was done by a group of humans.
The ground truthing, yeah, so there are these data sets, the city locations, the word definition, and medical indications, where there's ground truth there. And then we just generated the neither statements. Excellent question. But I like these kinds of triangle or ternary plots because it gives you an insight into like how well you are able to separate the probes. And again, this distinction between neither and abstain is interesting in that when it abstains, it's like, look, I don't like true, I don't like false, I don't like neither. I'm not going to make a decision on it because I'm not sure. I'm not more than 90% sure, right? My confidence isn't that high. And when it says neither, it's that it is 90% sure that it's neither, that it's neither true nor false. And so how do we create these neither statements? We don't know what the large language model saw, right? OpenAI is not going to give me their training data for me to see what the large language model saw. So basically what we're doing is we're creating gibberish, right? So we're using this Markov chain technique where for every word in the existing set, we're generating these n-grams, like 2 grams, you're seeing the ability, this is the 2 gram of the word ability, and then we learn these kinds of transition matrix of how likely is it to go from one token to another token, or from one 2 gram to another 2 gram, and based on that we make synthetic words. So these, and because of that, these are gibberish where we know that the large language model hasn't seen it. So here, this neither statement, this city is gibberish city, it doesn't exist, this is also. And so these are gibberish that we generated through this Markov chain technique. And we know that the large language model hasn't seen it, it's gibberish. And so it should say it's neither. So so I'm going to show you some results before moving on here. So for the correlation and selectivity results, we're seeing that, so this is the zero-shot prompt. Obviously, you want to be on the diagonals. This is the mean difference, and this is us. And in fact, if you allow the model to abstain, it will abstain. And so thinking about it as true, false, neither, and abstain is the right way of thinking about it. This is a more holistic way of thinking about it, where on the x-axis, you're seeing the performance, the MCC, with the multi-class sawmill. On the y-axis, here is the mean difference, and here's the zero prompting. And the 45 degree line is where like the two models will be performing better. Everything is under the 45 degree line, which means that the approach of probing with sawmill is better than those other approaches. Now here you may ask, okay, you're cracking open the box of these large language models. Which layers are you seeing that have the most veracity, have the highest veracity? Because we can train on any layer. And we have found this, others have found this, that the best layers in which the large language models can separate truth from false, from truth, neither, etc., is between like halfway to 75%. That is, after you go past the 75% in terms of the layers, so like if I have 100 layers, right, it's usually between the 50th layer and the 75th layer, where they're very good, their internal representations is very good at separating truth from falsehood. And part of the hypothesis is that as you go past the 75th layer, they're really overfitting. And so that's why they don't do as well. And since we had all of these different data sets, oh, and one thing is that for the neither, it's very good from early on, right? It's really just from the true and false that it needs more information. And then since we had all of these different models, we were like, oh, well, let's see how similar the different models are. So we did this minimum spanning tree of model similarity based on the layer-wise predictions. And what is interesting is that the leaf nodes correspond to models that are most dissimilar from the rest, and we observed that these default models tend to form leaf node, be the leaves, which is a separation from the chat-based models. The chat-based models are the ones that have the reinforcement learning with human feedback, and the Gwen models are among the most distant. So these are the ones that were trained on the Chinese data and the English data. And Gemini and Mistral models fall in between the Llama models. And this gets me to a point, my colleague Kathleen Creel has done a lot of work on what is called monoculture, that like a lot of these models are being trained on the same data. And so basically they're capturing the same things. And so if you go multicultural and multilingual, then you're capturing much better things. So what is next? What's next is the epistemic stability in this human AI society. As I said, there's this notion of what does a large language model know, what do you know, and then how does that change as you interact? So there has been lots of work on epistemic stability in people, and obviously what one knows is subject to stability conditions, and as Plato said, knowledge is tied down. So as I was saying before, there is a spectrum where maybe I cannot convince you that whales are a mammal, that like a whale can lay an egg, right? You're like, no, whales are mammals. Like, I don't care that you're showing me this video that David Attenborough has narrated that a whale is laying an egg. Whales are mammals, mammals cannot lay eggs. But then you get to this side where you're not maybe that sure, and your knowledge does not have as firm of a place to stand on. And so there's been work in philosophy, actually, by Hannes Leitgeb about stability of belief. And so we are inspired by some of that work in terms of what you know to be true, or what the large language models to be know to be true. Then when you discuss it when you have a discussion, or when you have a conversation with a large language model, what happens to the set of things that you believe to be true? In terms of epistemic stability in generative AI, Dan Dennett, the late Dan Dennett, the very famous cognitive scientist, called it counterfeit models. or counterfeit people. I like that notion of like you're talking to a counterfeit person. We know that they're not experts, so people treat them as one. They are probabilistic models of a knowledge base, right? I just mentioned the way of trying to figure out what they know. The one thing which is interesting is that they return to you what's most probable and likable. And there's a lot of studies about sycophancy in these large language models. And in fact, when OpenAI released the ChatGPT where they removed the sycophanciness, people didn't like it. And like, no, bring it back, right? I want a chatbot that is trying to please me, right? And we obviously don't fully understand or know them and how to control them. And this is what I was saying in terms of the stability. So you can think about, okay, this is the set of things that the person believes to be true. This is the set of things that the large language model believes to be true. Now I have a conversation with it. How much does it change the set of things that you previously believed to be true? And then you can have this kind of a spectrum between more stable to least stable. Another thing that we're looking at is relevance, this notion that we know that people make mistakes when something is probable but irrelevant, or something is relevant and improbable. And in fact, Kahneman and Tversky won the Nobel Prize in economics for some of their work here. And so since we know that humans make reasoning mistakes in this mixed cases, we're also trying to see if the large language models make these kinds of mistakes, reasoning mistakes in the mixed cases. And so instead of looking at when is the token with the highest probability and just removing that, we also look at the likelihood measure and the difference measure. And then for example, you can think of, I'm going to return not just the token with the highest conditional probability, but also return the token that has the highest conditional probability and the highest relevance measure. And a lot of the intellectual merit in this kind of work is how do you actually probe the large language model, right? Here's a system that has been engineered. How do you probe it? How do you set tests for it to figure out whether it will pass the test that you have for it? And then this gets us to the epistemic stability of people and generative AI, like how does the epistemic stability of an agent, person, or bot change when they interact? And of course, we have a hypothesis, and there's been work done here, where there is asymmetries between bots and humans, and bots and bots, and humans, right? And I highly recommend looking at Gillian Tett and some of her work. She's a cultural anthropologist. She's the provost at King's College in Cambridge and writes for the Financial Times. And she has in their surveys with DeepMind, she has that Gen Z, for example, 39% of Gen Z prefer to have a bot as a doctor than a human as a doctor. They believe that the bot is more objective and it's more convenient for them. And the same with respect to a manager or a boss. So, and we have known these asymmetries also obviously from the 1960s and the ELIZA model, and I'll mention that. But some of the things to study is the stability of the knowledge and the speed of change, right? Maybe if I tell you something, it doesn't change your mind as much, but if a large language model tells you something, then you change your mind very quickly. And then the other thing is to look at it as a group level and look at the group dynamics and how that affects our society, right? That can we predict when there will be a phase transition where a society that believed vaccines were good now believes that vaccines aren't good. And of course here, also we know a lot, as I mentioned from the 1960s, we know that people feel more comfortable with bots, and LLMs are slightly different in that, unlike social media, they want both your attention and your intimacy, and that's why they are a different kind of engineered system. And they never get tired, they never get angry, they're very good at apologizing. I'm sure you've noticed that, and they're people pleasers. And this gets me to the last bit, which is, this is really a call to action. So a lot of universities now have these partnerships or licensing with Gen AI companies. My university has a licensing deal with Anthropic and Claude. And so we know that students are using these generative AI models, these chatbots, etc., for their homework. homeworks and other things. And so that's one side. On the other side, we keep hearing about these AI tutors, right? And over the summer, I was talking to the CEO of McGraw-Hill, and they have done a lot of studies where surveys where they know that, oh, students are replacing going to a TA, etc., with like just talking to a large language model. And of course, universities see an opening of, well, maybe I don't have to pay for TAs as much. The problem is that there are no studies, there's no computational social science studies of how actually students are using these tools, right? And so, for example, at my university, I've had discussions with people about this, and they're like, okay, well, you should pass the IRB, and that's fine, right? The Institutional Review Board, fair enough. Then you have to pass the AI Review Board, that's fair enough. And then you have to get consent from the student, and that is fine. The problem is that if I'm gonna go and get consent from the student thinks, oh my, this is yet another surveillance on top of everything else, right? And they're trying to catch me for cheating, right? And so it makes you feel like, okay, the only way that I can really do this type of experiment is actually if I'm working for the generative AI company, because they have access to everything, and if you use it, you're giving consent to everything. The other thing that's a wrinkle here is that when universities use it, the data that, usually actually the data is with the tech company. It's not like, you know, they send it all to Northeastern or to Notre Dame, etc. Is that the data isn't filtered. So even if you de-anonymize it, right, and you filter, because like, think about it, a student who goes to Claude, it's not like they're like just asking about their homework. Maybe in the middle they're like, oh, I'm a little anxious, what do I do for anxiety? Or, you know, who won the US Open or whatever, right? And so you have to filter that for the course content as well. And so now that also introduces some issues. So for example, for the white paper that I wrote, it was like, okay, I want to look at first and second year courses across all different colleges, because biologists maybe will use it differently than somebody in drama, but then there are all these other hurdles. And for us in academia, we know about pedagogy, we know about teaching. So if in fact we want to help our students learn and use these tools better, then the computational social scientists among us should have ways of using this. And this is not new. I mean, if you were around during the social media era, it seemed like for certain studies, you really had to be an employee of Facebook or Twitter to do it, right? But it is unfortunate because there's all this discussion about AI tutors, et cetera, and we cannot study what is happening so that we can help our students. And then lastly, this came up in a lot of my meetings today, and you know, whether like computer scientists, AI researchers are going to have an aha moment, like the physicists had, right, with the atomic bomb, etc. And so we did a study, we analyzed the NeurIPS, which is a big conference, Neural Information Processing System. We analyzed the AI impact statements and ethics review for NeurIPS 2021, and it was a sad story. Basically, like in terms of the impact statements, a lot of them was like lack of agency, or like denying responsibility, or like assigning responsibility to the practitioner. There were a lot of like, oh, this is part of future work, but it's not clear who's going to do it. You are the one who knows your model the best, so you are the one who should think about it. There were ones, and I'm paraphrasing, like, yeah, the model can be used to hurt people, but look how cool the math is. Or, yeah, you know, the model could hurt the climate given how big it is, but look how cool the math is. And the ethics review was really just about policy versus not policy, right? It was basically like, are you plagiarizing or are you not plagiarizing, right? And a couple of years ago at ICML, for example, there was a paper on like how to use machine learning to improve automated weapons. And it's like, okay, is this something we want to publish, right? So again, it's like really thinking about what to do. And for that NeurIPS, only one paper didn't get in, and because of the ethics review, and that paper had really data issues. It was a data thing. It wasn't so much like, if the math is cool, the math is cool, and it gets published. And so the answer to the question is badly. So it's not like you can say, okay, no, the AI researchers are going to come and help us. And in particular, in that study and others, I feel like there's this notion of us versus them. Like, look, we generate the data, or we have the data, we generate the models, the math is cool, look at that, right? And look at all the good things that you can do with these engineered tools, and the use of it is them. And the key is that, like, we are them, right? These algorithms are going to be used on you as well, and the people you love. And so you should think about, should I do this? Should I measure this? Should I, go out and educate people and try to reduce the hype? So the way forward is education, and it's more a bottom-up education, right? Educate yourself, educate those around you, right? You learn something, you go tell your mom, and your mom will tell her friend, and her friend will tell another friend, right? To be able to be critical, be suspicious, don't give up your agency, and for God's sakes, reduce the hype. And the slides are here. Thank you very much for your attention.